All right, we are live for the Synacor challenge. This is part 2 of working on this, and we're not going to jump right into it. I think I'll do a little bit of a, let's see. Yeah, see where we are, and I think I'm going to do a little bit of a wish list for what we want to work on, and we'll pick things out of that list. So when we left off, we started modeling everything. I've got my notes here. So we have our basic opcode state or opcode enum, and then our basic VM state, which has memory and registers and a stack. We've modeled the 16-bit numbers. I think this is the first thing I'll want to work on today. Let me pull up that code separately. So here's the worksheet I'm playing around in. And yeah, so there's this number system that I think I'm gonna rename this to wish list. It's a wish list now. So we want a type safe number system. Um, type safe number system. And that number system, oh, is there a nice way to enter here? That number system, I'll just do this, needs, well, I think we need to stop modeling the low and the high byte, the little endian. So we need to transition away from that, stop modeling endianness. Let's see, we want operations that work just on those numbers. We don't want to be adding these to ints. So I've got a great idea for that, but we'll get there. We still need to implement memory properly. And then we need to implement the stack operations. And what else are we missing here? So to do register check. Oh yeah. Implement register operations. So we'll do that in some order. Hey, Eric Wastl. It's going well. Having a lot of fun. So started this off on Friday night and then took a break for the weekend. And we took a pretty relaxed approach and just kind of felt our way around and started laying the framework for VM state. But I'm really excited to work on this. Zuno, hey, welcome. Yeah, so I'm thinking about what we're gonna do today, and maybe we might, if we're at this for a couple hours, we might finish the VM state at some point where we could lead off next time with the first puzzle. How so here, in fact, I've got stream notes here in case you want extra detail. But the summary is that well, this right here, this code right here. So some of these are not implemented yet. So the stack operations are still kind of a to-do. We have the arithmetic operations, but I want to take a little detour and make that type safe. I don't like the way I'm modeling the numbers or the words, I should call them. So I'm going to use opaque types for that. And let's see, set for the register, push pop. So the stack operations, these are all still to do. Excuse me. No, not yet. I mean, maybe this could run it, but no, just start off with modeling. Let's pull up the spec. Well, we'll pull it up when we need it. So for now, Yeah, let's get into this num. So here's my thought here. The binary does things even if you don't have all the instructions. Okay, that's good to know. I imagine, yeah, I imagine the first program is just like it prints some string. Uh, so it probably doesn't even need to do much math or anything. But I'll keep the suspense. Um, so the number format we have, I'm going to formalize this a little bit. So we have a few types. There are 16-bit values. So this is basically what I've been using num for, is just encompassing all of the values. Actually, I'm not sure. Am I doing? Yeah, I'm using num as 16-bit little endian. And I'm modeling low and high byte. I think I'm just gonna leave that in the binary and parse it into like an int. So we have I'll call it word. So we have a word, and then we have what other types? Um, we have all numbers are unsigned integers, 15-bit. So we have a U15. We have addresses and we have literals. So address, oh, let's upload this, and we have literals. And all of these are going to be backed by ints. So right now, these are just type aliases. So over here, a type alias on the bottom left. So type alias like this here, memory, just says that it's a map of number to number, but those are interchangeable. So this doesn't actually give us any type safety. This is just a convenience to shorten types. And it does other things. So like types can actually be functions too. These can be function types, where like this has a type parameter that you do something with. But really, they don't give us much type safety. Um, so I think I'm eventually going to replace these types everywhere where appropriate down here. But what I'm going to do is do this with opaque types. So let's open up a proper file. We'll put it in here for now. So an opaque type, let's put this in. I actually want to put this in a package. I'm just going to use this file for now. So I'm going to take an opaque type alias. Outside of this package, Synacor.numbers, these types are not treated as equal, so you can't use a word and an int interchangeably. So I'm going to do a little bit more here. Addresses and literals are both U15. So I'll say that they are subtypes of U15. Maybe that's a foot gun, but we'll see. And I guess U15 could be a subtype of a word. We have time to reconsider that. So now over here, if we were to import that, well, over here you can add a word and an int. But if we were to import it over here, we would get a compiler error. But that's not very interesting if we can't actually do things with it. So the way we add methods to this thing that looks like some random types is with extensions. So we'll do an extension on the literals because that's where we'll be doing most of the math, right? No, n is a lit. So we can define our plus and fix the plus, another lit. Actually, let's make this a and b. B lit and returns a lit, and this is going to be just a plus b, and it's just integer a plus b. Integer a plus b with some masking. So let's see what we're doing previously as far as masking. Yeah, I don't like that. So these are 15 bits. So that is 0x FFF is going to be 16 bits. That to be 3 there. So we have 7 FFF. So we're going to end it with that. And then we're going to do similarly for all these other operations. And same mod. This is a place where I should just turn on Copilot and let it autocomplete. And then same with the bitwise operators. We'll have Copilot do that autocomplete and fix def. And there we go. Or and oh, oops. Greater than, and then this not. So this not, if we want to have this prefix syntax here, we define it as unary. I had to look this up. And then this is a special name that's treated as a prefix. And I don't know if we need to. I think we do need to mask it because I want the first half to be 0. So yeah, I'm gonna mask that even with a not. And the equality check, I don't think we need an equality defined. Okay. So let's try that out. I'm going to import here. So import synacor.numbers.star. And then, oh, we don't have a way to create values. So let's do that. This is a, oh wait, this method here needs a parameter. Oh no, it does not need a parameter. That should be good. Okay, yeah, that should, well, hold on. I want this to return a lit though. That's invalid syntax because this is just a method name, and after a method name, you can put, I know. It has to have no parameters. Okay, well, I'll do the casting on the other side. So this thing that it's returning is a lit. There we go. And then we need to be able to create lits. So let's do object lit, and I want to turn off Copilot here. And we want a from it. The from int returns a lit. And it would just be n, but we want to do a check here. That's not, that is valid. So this is a max value, right? Just all ones. So we'll check. That n is less than or equal to that. We'll make it an assertion. Whoops. There we go. I am very excited to get to the part where we run the VM and find the other puzzles. But I like that there's no clock, there's no leaderboard, so we can be relaxed about it and make it nice to work with. Okay, so we can do now lit dot from 3 plus lit dot from 4. Oh, from int is what I named it. X equals that. And we need a method for parsing it from bytes. So def from, oh wait, no, we should do that for Word specifically. So we'll put this up here, object Word, def from byte, bytes. So we have a low byte, low byte, a high byte, and this returns a word. And if we do we have a similar method defined already? We don't. So we're going to make an int and then cast it to Word, essentially. So this low byte, we are going to want to, the byte is signed, so we're going to want to mask that. And we are going to OR that with the high bytes shifted left. So high, I guess also masked. I think we want to mask it before shifting, because if it's negative, hold on, if it's negative and we shift left, I suppose we can shift left first, can't we? I'll need to double check that. So we're going to shift left by 4, and then we're going to mask it. Okay. Oh, no. There's a 0, 0 there. I'm still somewhat worried about shift. Like if it's negative, then all the leading bits are going to be 1, right? So if we shift left 4, well, those leading bits remain 1. We fill in the right side with zeros. I think that's fine. GG verify. If someone sees it, I don't mind hearing what it is. Okay, so we've got a system, and great, we are able to add 2 lits, but it's returning an int, which is not what we wanted. So let's make sure that's asking for a lit. Okay, I don't like that it's upcasting automatically. I don't think that should be able to happen. Right, like if I make this an int, that should be an error. Or if, if I do val y lit equals 34, 1, 2, 3, 4, some int, that should be an error right there. Okay, that is an error. Okay, that's good. I'm satisfied with that. And now addresses. So I thought a little bit about this. With addresses in here, we do add them. So if program counter is an address, and we, when we progress, we skip past the numbers, and when we get the arguments, we increment that as well. But I want to keep that pretty limited. I don't want to be able to do arbitrary arithmetic and then get a literal out of it, right? Otherwise, you might accidentally use in the wrong spot. So I was thinking about just limiting that here explicitly. So we have an address. And we can just define, the only thing we're ever doing is adding 1, 2, or 3. or I guess 4 to. So we'll just define those methods. Def inc returns another address, and it's just going to be a plus 1, right? We can multi-align that. Oh, so we have 1, 2, 3, 4. Cool. Very limited. That's all we should ever need. And of course, like these can all just be inline, so we can make that an inline def. And then the compiler could probably optimize that further. Great. I think we can be happy with that for now. We'll probably revisit that as we see what other methods we need. But we want to make sure that the boundary here between when we use the memory and whatnot is all safe. We don't want anything exposed down here. So this dot store, we have a store method, a helper method. So we have a pause, which is a num. This should be an address. What I'm going to do here is just do some temporary aliases. So let's not import these numbers just yet. We're going to rename num to word. So rename that to word. And then we're going to add some aliases. So type address equals word. And same for lit and U15. That way we can start putting the right type names in the right places. And let's see, we want the spec. I want to put the types in the spec here. So that I know what I'm working with. So say, let's start with add. So assign into A the sum of B and C. So A can be a register. I think A is probably just a register. So A is a register. B is going to be a literal or a register, I think. So A is a register, B is a literal or a register, and C is also literal or register. Okay, so that's going to be similar for all of these operations. So let's look at something else. When you push A onto the stack, A is probably a lit or a register. Let me make this clear here. That's probably good. Okay. We're pushing a literal or the value inside of a register. So the register we're going to dereference. Pop is going to remove the top element and write A. So A is just going to be a register. Equality is going to be similar. This is a register. And then we have B or C. Just more lit / register, just like add. Jump, this is going to be an address. Jump true and jump false. So in this case, A is a lit or register. and B is going to be an address. Is that right? If A0 jumped to B. Okay. And what was the other branching thing? Oh, I want to look at read mem and write mem. So read the memory at address B and write to A, which I think is register. And write the value from B. So B is the value. So this can be a literal or a register. And write it into the memory address A. Okay. I'm assuming we're not able to just write it to a random address too. Maybe it's a register or address. Or address. Not sure about that yet. Well, okay, this is reading from. Read the memory address B and write it to A. It doesn't say A is an address. Yeah, I mean we have write mem for that, so that wouldn't make sense. And for write mem, read the value at from B into memory at address A. Is B possibly a register, or is it from B? I'll say B is a register. And I'll say it could be a literal too, but I'm not completely sure about that. Okay, this is an address. And yeah. Okay. We have our spec updated. So let's go back into here. And let's look at our write method. So def store. So at position, I'm going to rename this to address. Rename. Oh, and this is an address. And we have the value, I suppose the value we're going to want to store is going to be a literal. But might we want it to be a literal or a register at this level? Or already, let's assume it's already dereferenced. Okay. We can just shorten this to A. And memory is still a map. I don't think we need to implement memory just yet. As long as this works, and this is the only place where we're using the fact that it's a map, then we're fine for now. Although, read mem is going to be the value at A. I'm hoping we get type errors here once we import our actual types. Because I don't think this means like store into memory. I think this means store into a register. Okay, let's look at how we're actually going to use this. So at this point, when we're parsing arguments, these are all words. And we're going to have to do something like A here. So this would be a register, right? So we're going to have to do like .reg. So I'm going to implement these as extension methods on our word. Um, and we'll have. You're almost done. Oh, have you been working on Synacor too? Are you saying I'm almost done? So address, for now, these are just like stub methods, but later they'll actually convert it and do the errors. So that's just gonna be word, but it casts it to address. And then lit and anything else. I guess there's a register reference, which we'll also have as a word for now. So let's go back to our type. It looks like I'm almost done. It looks close, yeah. Like I think we can get there and have it like fully implemented and start doing some testing. I mean, we can test it just by running the code, but like I also kind of want to like play around it a little bit. We spent all this time building it. Okay, so great. Now this is what this is going to look like. We have we're storing into a. Oh, our store method is bad. This should actually be doing. This should take a register. Right, anytime we're saying store in here, so like for add in our spec, assign into A, oh, assigned. But for mult, it says store into A. I think A is a register. So this method that I've actually written is write. So we're gonna call that write. We're gonna keep store, but now this is our reg, and we're gonna leave this unimplemented for now. We do have a system of registers, but we don't have. Yeah, we can implement that later. As long as we get the method names right. So this needs to be a register, and there's a literal value. I think this value is a literal or a register. No, let's say it's a lit. And then we can just have a method that will dereference a register if necessary into a lit. Okay. You'd like me to explain to a noob what I'm working on? Well, that would prove that I understand it somewhat, right? So there's a compiled program, and the compiled program is all just binary, right? And we don't know what this program does because this is binary for a foreign machine. It runs on a different kind of computer than we're used to. So this program has a bunch of puzzles hidden inside of it. So in order to get to those puzzles, we first have to make a machine that can run this program. So all we're given is a specification for the machine, and we're implementing that. Um, yeah, so we're reverse engineering a binary. So let's start using this. So store into A. So this is going to be a.reg, the value of B plus C. And I'm going to say that these are literals for now, but I'm not convinced that they aren't. We'll get there when we get there. I'm not convinced that they aren't, well, maybe I'll get a method called value. So let's do a method on a word called value. That will give us a lit either way. And like if it turns out that all we want is lit, then value can just be renamed to lit. So value, this is going to return a lit by first to do the reference if register. Yeah, the bin file's in my repo, but the challenge, yep. I've been using a different fork. Zuno had a fork too. All right. So now we can just say b.value plus c.value, whatever the value eventually is. It might be, it might end up being just a lit. And since all of these share the same structure, we can just multi-line this. So it's going to be a.reg for all of these, and then b.value, operator, c.value. Yeah, that's the purpose of reverse engineering. For fun, for practice. It's a challenge. It's a puzzle. So here we store into a.reg, the value of b.not. Oh, we have a unary operator now. I'm going to rename that not. So def not. This can just be, I set rename symbol to unary. Oh, that's what's happening. When I was putting in the colon here, that was part of the name. So there has to be a space if you're doing a type. I see. Okay, so now there is just, we can just do not b dot value. Cool. Let me catch up with chat for a sec. So Zuno, you need to update your solution to work with Aneurysm's binary. The binaries differ across accounts. Oh, okay. Wait, why would your solution, your solution code or puzzle inputs? That makes sense. Alrighty. So let's look back at this here. Read mem and write mem. This is actually gonna be store. Or not, no. Read mem is gonna be store. Because we're storing into a register, right? Write it to A, the register A. But we need to like dereference. We need to read A. So let's give ourselves a little read function. So def read, given address A, we're going to read out a word, and it's just going to be memory dot, oh yeah, just get A there. So now we can just read A, and that gives us a word, which we will then store into B. I'm wondering if read A should just return a word. I think we're allowed to just do an arbitrary word. This isn't supposed to be. Well, hold on. If B is a register, I'm not sure if registers can hold arbitrary words or just. So 8 registers. I'm gonna guess that a register holds an arbitrary word. So it doesn't need to be a value. It doesn't need to be like a lit. Okay. And we are getting errors, which I think is good. This is weird. Nothing required what? What's the return type of store? Oh, right. Yeah, its return type is literally nothing. Um, it's going to be an updated state. So that's going to be this.copy of some sort with updated registers. So this.copy registers equals just registers for now, but we're going to modify that. For reference, I am this state is completely immutable. So the idea is that I can just go back forward and backward in state. I like doing things immutable, and I'm pretty sure the performance will be fine. All right. So back here. Great. Now when we're storing, we read from the address A, so A dot address, and we store in B dot register. And then now when we call write mem, we're actually going to do write, and A is an address and B is a what? A literal. So dot value. Okay. And jump. So program counter is an address. So we'll do A dot address. Like, and then this would fail if a address was not if like this word was not an actual address. So same here with jump true dot address dot address. I should have, what I'm going to do is make this its own helper method. I'm going to put down the right side here. So we have read, write, and store. Store is for the registers, and then we have progress. I'm going to put progress near jump. Because they are similar. So jump, and given an opcode, it doesn't need an opcode, it just needs an address, a address, and we copy and say program counter equals address. Great. So now this just becomes jump to a dot address, no output. I'll catch up in chat a bit. All right. When you click download, it would go through and compile it fresh just for you. Ooh, cool. I figured you might have a compiler. I don't know if we'll have to implement a compiler for this, but I low-key want to like do some simple language for that. It's been a while since I've done it, but I feel like I can do it better these days than I could back then. I might at least write an assembler so that I can write test programs in assembly code. And maybe, I don't know, maybe it'll call for a disassembler. That'd be cool. You do an assortment of things in this challenge. I see Black Deep, hello. Yep, we're streaming. We're gonna be streaming every weeknight this week. I hope to have this done by the end of the week, but we'll see. It's a Christmas miracle. We might get more Christmas miracles. We'll see. And stupid gladiator, you're working on FPGA logic right now. So what you're doing is not that far apart, writing a system in Verilog. Cool. You'd buy an FPGA and write the logic you're writing right now in system Verilog. Yeah, actually, it would be kind of cool to implement this on actual hardware, wouldn't it? So if you have a system you can recommend, that might be a fun toy project for the future. By the way, stupid gladiator, have you heard of Advent of FPGA? So this is just Jane Street, and the the challenge here is to take an Advent of code problem from this year and implement it in FPGA, and then you submit that, and they do code review and choose favorites. So here's the link in case you're interested. I'm thinking about doing that after this. So stay on kind of a similar theme. Yeah, are there free Verilog tools? If you have recommendations, let me know. I need a stack. I need both a software and a hardware stack for for that kind of stuff. And looking back at this, I think I think we might be done with this part, with giving everything like the types we want. Um, I think this 1 and 2, we want those to be literals. I might rename tunum to toolit. Oh, there are a couple more here. So we need to rename A in the jump commands. Yeah, we still have more renaming to do. So when you're jumping, let's look back at the spec. If A is non-zero, so I think that's just going to be a lit or a register, which means dot value. Dot value. Which means what it's checking against has to be a lit. I would be interested in hearing about that. So to num, I'm going to rename this to lit. And we want, what do we want? Lit as return type. And for now, this is the implementation, but we will change that when we get there. Okay, back here. So that's now all to lit. Here, when we store, that has to be a register. And x is going to be the value. So x is already a value. We'll just make that explicit. And if b equals c, so is it also just comparing two values? Let's look at greater than. If b is greater, yeah. So b and c are both values. And I don't know, they could be words, but you couldn't, the argument couldn't be a register if they're just, if you're just comparing the words. And it doesn't make sense to compare words. The comparison operator exists on literals. So these are values. Okay, are there any more of these to cast explicitly? Output A, oh, we'll need word.ascar. So A, we'll say to car. Well, I mean, we can say as car, as a character, because there's no conversion that needs to be done. It's a character is going to be 16-bit. The word is already 16-bit. We have extension methods on words. Extension on word. So we'll add ascar here. Def as car. And since a word is just an int, oh wait, no, a word is not just an int. Isn't there a w.2? Did we implement? I don't want to give an actual implementation because our actual implementation is going to be on the other side. When we use the actual opaque types for these instead. You know, that's fair enough. I imagine there wasn't like a whole subreddit and community for Synacor. Stupid Gladiator, you have that recommendation. Okay, I'm gonna take a look at this. Oh, and thank you for the follow. Let me just pull that up in my tabs for later. Actually, this is how I want to do it. Okay. Project Ice Storm. For FPGAs. Okay. I'll have a look. Thank you for that. Okay, so everything's compiling. Now the goal here, what we want to do is start using these and hope that everything still compiles. So where were we doing our type aliases? We're going to comment those out and we're going to import synacor.numbers.star. Word.from it. There's no from int yet. So we have from bytes. Let's implement a from int. Def from int. And I think it's going to be fair just to cast it. Because our words in memory are big endian. This is the only time when we worry about the little endian, is at the boundary when we're looking at individual bytes. So we'll want to do a check that is 16-bit. So we'll require that n is less than or equal to the max value for words. So that's going to be 0xFFFF. Yeah, and then we just return n. Oh, and that gives us our 2lit on integers. In fact, this method should probably just be moved into this file here because it's only really relevant whenever we're working with this number system. So we'll put it here. Working full time. I work contracts. So right now I have another contract starting in January, and then I have free time between. Okay. What else fails to compile? Registers. Why is that not compiling? Oh, we have a situation here. So address, this copy PC, a word was expected. So up here, the type of this should actually be address. Okay, and then PC plus 1. I think we're just gonna increment. And I suppose we need to match the number of parameters to decide which increment function to use, which is a little bit silly, but that's okay. So op.numparams match. Let me catch up here a little bit. Yeah. I mean, there are already lots of things you can do when you're just given a VM spec. But I'm curious. I'm curious to see what comes up next. So if there's a 0 params, then we will just increment once, right? So a.increment. And I guess we could, well, this dot copy and PC equals a.increment, right? That's a general idea. And increment 1. It always has to increment at least 1 to get to the next instruction. So 2, and we have 3 down here. And again, 1, 2, 3. Oh, wait, no. This is actually 2, 3, 4. 2, 3, 4. Okay. Oh, wait. Number of params can be. Do we have inc 4? Yeah. Inc 1 is not a member of word. Wait. Our parameter A should be our current address, right? So it's just going to be pc.inc. That makes more sense. Okay. And then now these. Get the words from memory. Okay. Again, it's just inc 1. So inc for each of these. I can multi-line that. Piece dot inc. There we go. Inc 1, 2, and 3. Okay, we still have a to do for memory and register safety. Let's find the next error. Memory. Oh, memory now is wrong. So memory needs to be a map from address to word. Okay, cool. What's wrong now? We couldn't find a type called register. Ah, yes, we haven't implemented register. So opaque type register, and we'll just say it's a word, and that's all we'll say about it for now. Or it's a subtype of word. Great. Now these extensions on Word probably should just be moved here because we'll need to do some sort of casting. Okay, so we'll do that in our proper file. Yeah. Now we can give these proper implementations. So if we're taking a word and turning it into an address, it's the same as turning an int, right? Do we have actually a constructor for address? We don't. How are we going to order this? So we're just going to do generally words, address, literal. They could be separate files, but I can always organize that later. So we have an object address, just going to add methods like from int. And now we have to check int return an address, and we have to check that it is 15-bit. So we're going to require that n is less than or equal to the max 15-bit value, which is going to be 7FFF. At this point, I should just name that max value like u15.maxValue. Yeah, let's make it more explicit. So U15. So it'll look a little bit like how int is implemented, right? So you can do like int dot max value. Um, so val max value is just going to be 0x7fff. That might come in handy later. So this returns another U15. So U15 dot x value. And we can just do a find and replace for all of those. 0x7fff. Oops. 7fff is going to be U15 dot max value. Great. Did address from int need to return an n? Yes, it does need to return in value. Thank you. Cool. Now that was a diversion from actually implementing one of this. So for this, we can just do address. Yeah, address dot from int, and we can pass the word in there. And again, because this is the file where the opaque types are defined, it already knows that a word is in fact an int. And we don't have, this is a place to do all the unsafe casting. And we don't do any casting anywhere else in the program. Great. And we have a similar thing for lit. I'm just going to copy. I think I'm just going to make the implementation in U15. And this returns a U15. And then address and lit can both just defer to that definition. So we can do U15 from it. And there we go. Same thing for our literals. Okay. Oh, we already had a U15 from it defined here. Great. Well, now they're using the same definition. So if you want to add an error message or something, there's only one place to add it. Great. Now we still need to complete the rest of our conversions. So now lit is just going to be address dot, or I guess lit dot from int. I suppose for all of these, I could just written U15 dot from int. But that might be nice to have there for like the external API. And register, that's still going to be a to-do. We're not going to think about registers for now. And value. So a value needs to, oh, this dereferences the register. So this, I think, shouldn't be defined here. Define in VM state. Yeah, I don't think this is the right place for that. But we'll leave that as a stub. And now character, it can just be int to character, w.to character. Cool. Yeah, so much easier than working with the weird class I had before, which I'm going to delete now. So we had our word class with all these master definitions, which I'm not even sure are safe, from like overflow and signed, unsigned. We can get rid of these temporary type aliases. clean things up a bit. Uh, cool. And why don't we just put our import at the top, like some sane people. Okay, so now we have our opcodes. We have registers, which we're gonna get a better implementation for later. Stack and memory, we'll get better implementations for those as well, but a map from address to word works. And then our state, we can move around, we can output things, we can reference arguments, we can read and write in memory, and we can store to registers. Okay, now these we don't need, except for value. This is where we the reference. We'll keep that as a local definition. Mm, we're just gonna do word dot to. We're not gonna implement this yet, so we're just gonna do dot as instance of lit so that the compiler's happy, and that's just gonna be big to do because that's almost certainly an error. Okay, any other compiler errors down here? So read. We found a word. We required a lit. We required a lit because we are storing. So when we read from memory, we do read a word. So we're going to do dot lit here. Okay. And as character, A. Oh, so A, first we have to convert it to a word, I suppose. Wait, A is a word. And as character defined. So what's the issue here? We required a word. Oh, so when we output, what we're outputting should be a character? No. No, we can, I think having it be a word is fine. And then we do conversion to character here. Okay, we'll rename that to W. And in where we call output here, we just output the word. Okay, we're back to compiling. So now we have safe types for our U16 words. Yeah, that feels satisfying. Now, I think I'm still happy with our memory implementation. And we need to start thinking about registers. Let's look through our to-dos. So we have our stack operations. We probably won't need that yet. We have, this is more stack related stuff, call and return. And out and in, so output needs to progress. So we're gonna do this dot progress. I think that's fine. I think I was unsure about modifying the state before doing an output. Because when we output, it's a parameter we're passing. So output doesn't require rely on like the current state. Okay. So time to store in registers properly. Superviz, hello and welcome. Mm, yeah, we'll do register operations. And then I think we might go ahead and do the stack operations after that. and then we can start extracting output from our binary. So our store, this.copy registers. We'll need to be able to even parse what a register is in the first place. So let's go back to our number system and implement that. So let's start with a register.fromWord function. So we know it's the first 8 values. It's an object register. Or, we can just make it from it like everything else. Def from int. And it's going to return register. I kind of want to use the fact that there are only 8 register values. Maybe we can say we could make register an enum, and we can name them R1 through R8. I don't know. Let's be honest with it and just keep it as a number for now. So we require that it's within a range. So 2 things. Max value, u15 max value is less than n, and n is less than that plus 8. I can write it this way. U15 max value to... No. Let's do this. Plus 8, so less than or equal to that. And then just return the n. Okay, that is our register type. Value less is not a member of U15. Oh. Well, I mean, that should be fine because U15 is just an int. Right? Like, where was that defined? That was defined right here. So this is all defined in the same scope. We know that U15 is an int. Let's do to int, I suppose. Eesh, I guess we can do it as instance of int. Where's max value defined? It's defined in here. So I suppose maybe outside of this particular scope, it's not known that that's actually an int. That's not how I thought the opaque types worked. But in this file, we can do unsafe stuff. So in this file, we'll just do it as instance of. Okay. It's just for an exception check anyway. Or you know what? We can make it more explicit. 0xf. So this is the max value, right? So that's what we want to be. Oh wait, no, that's the U16 max value. Yeah. Or we can write the full range. So this 8000. So it's gonna be a 1. Is that 8? Yeah, 8's gonna be in the 4th bit. So 1 followed by a bunch of zeros, by 15 zeros, is the lowest possible value. And then the highest possible value is 008, right? No, 7. Okay, I like this better. This is that feels more understandable to me. Okay, now that we have that, let's go to our registers class. Um, oh, in our worksheet class, registers. Oh, Z.A. Shah, welcome, welcome. Thank you for the raid. We are working on Synacor. There's a link here to my repo with some explanation, but basically what this is it's a puzzle in the form of so we're given a binary and we're given a VM spec. So the puzzle is hidden within this binary. So first thing we have to do is build an emulator for this VM that's capable of running that binary and seeing what the output is. Then we'll see what else what that says and what else is hidden in the puzzle. Yeah, making a VM. Um, Specifically an emulator, but yeah, it's for the Synacor challenge VM. Yeah. So if you're familiar with Advent of Code, the Synacor challenge was made by Eric Wastl in 2012. Um, so there's been some like reverse engineering type problems in Advent of Code over the years. In 2019 in particular, there was a VM that you implemented. So it's similar to those puzzles, except just one like I think it has 8 nested puzzles inside of it. But before we even get to see puzzle one, we have to make the simulator. What were you working on? Um, yeah, and if uh, that link there has my stream notes from last time. So this is part two. Basically, we're about to finish the implementation of our VM state, and then we'll move on to like using that VM state to actually run the emulator. Okay, so registers contain, I guess they contain arbitrary words. I want to rename these just to R1 through R8. Or I guess R0. That way it aligns a little bit with the actual physical address. Because we already use ABC for parameters. Whoa, what am I doing? Okay. 4, 5, 6, 7. So you were doing a smattering of things, checked out projects from a bunch of people, then did some Bevy, Rust, and working on your own game in C++. Cool, cool. Rust has been on my to play with list. I'm doing this in Scala. And now, oh, we have to change these values here. What I'm going to do is just copy this and just do like a multi-line edit. There we go. Now we have a parameter list. Okay, so apply given an index, we return a word. I think what we actually want is apply given a register index. So R reg, then we return a word. And then we could just do reg to int to index into that array. Yeah. R dot to int. And actually, you know what? I want to think about that a little bit more. For now, I'm just gonna do this as instance of int. The thing I said I wouldn't do. Unsafe casting outside of this particular file. Because I'm not sure how I want to implement this yet. This counts as a double definition, right? Because those erase to the same type. Oh, here's what. Oh, I wonder why they're actually erasing to the same type right now. But anyway, we're not going to do this with ints. We're going to do this with the register reference. Word. Yes. They are all words. I mean, I'm not sure when I'd actually want to like reference individual registers like this. So maybe this should just be backed by an array. Um, but as long as it's encapsulated in its own type, you can always change the definition later. Now we can start using that. It's an octet of octets. I guess an octet of double somethings. Alrighty. So we use registers when we're storing to a register. So in this case, registers. It depends on the value. What we copy depends on the value. So this is making me feel like I should have, like, I'd give myself an easier time if I just make this an indexed array. I would have an easier time. I don't think I need to reference individual registers by anything except, like they don't actually have to have a value in an object. Registers.copy. Yeah, the word that we update depends on the value of the register. I'm going to add an update method. So no matter what the underlying implementation of my registers class is, we're going to have an update method that takes a register and then returns a word. Or I guess returns a new set of registers with that word updated. Update R to value. There we go. We'll call it updated. And we'll go back to our definition of the registers. Def updated at R. With the value here. And that just returns a new set of registers where it's up where the values update appropriately. So I'm commenting those out because I don't know, maybe I want that in the future. But for now, we're going to do val, or no, we're just going to do like underlying. So the underlying type here, we're just going to use an immutable array. So an immutable array of words. And I suppose for a constructor, we're going to require that the size of underlying. So require underlying dot size is equal to 8. So that's an invariant. We never want that to change. And this values we don't need anymore. We can just do underlying and index into that using our reg value here. Okay. Now I'm realizing here our reg values are actually not 1 through 7. They are 8001 in hex through 7. So we need like a toIndex method. So we'll do an extension on our register. So def toIndex, and it's gonna be an int. And we just need to take off that leading one, right? So we can end that with just a 0 followed by 15 ones, right? So toIndex returns an int. We take R and we mask it with 0, 0x 7 FFF. Yeah, I suppose we could do this with an OR as well. We could OR it. I think I like ORing it better. So a leading 1 in that 15th place. No. We want to end it. End it with that 0. Cool. Right. I feel better about that. I didn't want to do a 2int here. I don't want to just have like a bunch of random 2ints, really. I want to convert it like with a purpose. So we can only ever do this to an index. That way we're not accidentally using things as things are not supposed to be. So the r dot to index, we got rid of that unsafe cast. That feels a lot better. Cool. So now we still need to implement this. V value is going to be, oh, I suppose we can update it with an arbitrary word, can't we? Yeah. So this can be underlying dot updated at the index r dot to index, and we just place word in there. We required registers now. We actually have to wrap that. So we're going to wrap this in registers. Great. Now the one last thing I thought of here is, well, we need a constructor. So object registers. So we're gonna do def apply, and now I think we'll do it this way here. So this will make it nice. This will make it nice for creating custom registers for testing, or maybe we're doing that in a puzzle or something. So this gives us a new registers, and it's just going to be these underlying values. So I'm glad I didn't delete that and just commented it under a new set of registers. Cool. Now we can delete all of this. Nice. I'm feeling much better about that. Now let's actually use it down here. So in the registers, we have store in a register, a lit. Now updated takes a word, but a lit is a subclass of is a subtype of a word. So that should be safe. Now we can also do set. What does set do? So let's look at the spec. Set register A to the value of B. Oh yes, and we can start like dereferencing registers now. So we can implement that value function. Now set, so we just store then. Store in a.reg the value of b, b.value. And then there's no output. And we also progress. Okay. push and pop or stack operations, so we'll say that for later. And I think all of the register operations are complete. Now we just need to make sure we are dereferencing things properly. So the word is either a register reference or a literal. We can't get the value that's in that register without having these registers in scope. I think I would like to have that a lit or register function separately, because I don't want to do that bit checking here in this file. I want to have that in our numbers file. So let's go in here. Yeah, we're going to implement a method called value here, and it's going to return either a word with either a literal or a register reference. Reg or literal. And I hope that union works fine outside of here. Then we can like match on that, right? So basically, if the first bit is set, the leading bit, so if W, how do we check this? We could AND it. I guess we could. Yeah, we can AND it with 1 followed by 15 zeros. And check that is 1 followed by 15 zeros. So in that case, it is a reg reference. Then you return W as a register reference. Great. Else we return W as a lit reference. I don't like that. We're basically just casting the word. I think we do reg.frontend. Pass along the word. Otherwise, we do lit.fromIt. Okay. That I am happier with. And then we still want to dereference that. Oh, what's going on here? True require. Oh, we need I suppose we need friends here. That's the operator precedence, huh? Okay. So now we need to be able to dereference. So dereference a value. We'll just say v val. No, value is a register or a lit, and we're going to return a lit. So now we can do v and match on that. So case register. Let's start with the lit. So if it's n, that's some lit, then we return n. I guess it's not necessarily a lit. It's a U15. Because maybe it might be an address. Usually when it's used as a value, and we don't do arithmetic on values. So I'm gonna say that this is a lit. So case R, that's a register reference. In this case, we do registers dot apply. No. We take our local registers and we just index it by r dot or just r, yeah. And that gives us a word. So I suppose a word needs to be converted to a lit. I think register should contain words. I'm not very sure. Do registers? So we'll leave this as a to do. So do registers actually contain lit? And we can double check that later. If we have runtime crashes, then that could be one of our issues. So a word, we downcast it. We can do lit.from int. Actually, give me a second. I'll take a little break and we can think about that later. All right, I'm back. What'd I miss? 100x programmer, welcome. I am a fan of this VM. It's cool to have these small instruction sets. So there's a similar puzzle. I'll open that in our links to take a look at later. Whoops. And yeah, that makes me think of have any of you heard of the elements of computing systems or NAND to Tetris? That was basically a project where you started with NAND gates and build your own computer and then like a compiler and like games on top of that. So the whole kind of a tech stack starting from logic gates. And at each step, it was like a simplified version of what you'd actually do, but it was like simplified in a nice way. It was a very pretty architecture all the way through, and great for learning. I'd say it was like one of my formative experiences as a programmer was running through that book. You did an end to Tetris. You did just the computer parts. You didn't get to the compiler. Um, I I got through the compiler part. I didn't do the Tetris part. I didn't feel like I don't know. I mean, Jack was a language, and you could use it, but I didn't really want to use it to. And it wasn't really like running on your whole own architecture, right? Like at some layers, you then needed to use like a faster implementation of like what you'd implemented beforehand. So I didn't need the satisfaction of that bit, but doing the compiler was fun. It sounds like a crazy amount of work, but the way it's laid out, it's very approachable. I did the whole thing in 2 months. So what I did was this was set up so I could be like either a 1 or 2 semester course. And what I did was I dropped out of college and then I did that for the next 2 months. Because otherwise, like the way my college's schedule was set up, I would have had to wait another 2 years to do a compiler's course, and I wanted to do it right then. Um, the same thing was happening in my math classes or classes I wanted to take. I could just get the books. So like I don't know. I didn't drop out completely. Like I left to do like a independent study and just do my own stuff, like read the books I actually want to read. Um, and then I ended up getting hired by someone. But the first thing I did when I dropped out of college was do Nanta Tetris in those 2 months. And like I was really immersed into it. I was having dreams of dreams of compilers and shit. Um, and yeah, it was a good experience coming out of that. So, where are we? You played, let me take a look at that game. Is this a Zachtronics game? MHRD, a hardware design game. Okay, cool. Yeah, I like stuff like this. I think if I were to stream games, I would stream some Zachtronic game, and I'm thinking about Shenzhen IO. Uni's gotta step it up. Yeah, totally. Totally. I went to some small liberal arts college. Um, And I should have gone to like a proper university because like part of the problem was like their scheduling. I couldn't even take the science classes I wanted to take because they all had the same Monday, Wednesday, Friday block, and it was just and then like the annual blocks too were just a pain. It's full of a bunch of spoiled rich kids who were complacent and didn't actually want to like nerd out and stuff. So not a good fit. Um, yeah, where are we? We are dereferencing a register. Okay, so our register takes a register and uses that index to get a word. And if we were dereferencing as a value, we do have to do the checks, right? If it really is an arbitrary word that we're storing in there, store. Like we can set every other time we're storing, it's after an arithmetic operation, so it really might be a lit. Um, So I'm kind of tempted to just take the shortcut and see what happened. No. I want an error. I want an error if we um, got a word and we're expecting a lit. So let's use a method here. So we could take our word and we could do .reg, right? Of course, we already have a method for that. So no, not .reg, .lit. Yeah, we already have word to lit. And we'll leave this question for later. Basically, if this line ever crashes, we look at this to do. Okay, now we can dereference a register. Set. No output is not member. Oh wait, we need to progress by whatever opcode says. Okay, are we back in the compiling state? No, this needs to be an immutable array. Okay. Okay, we're back into a compiling state. We have a way to dereference. But where do we actually need to use that? Yeah, we store a lit. We deleted our .value method because, well, actually we have a .value here, and in terms of register or lit, I think we need to dereference that before we attempt to store it. So all the places where we've stored, case n. Oh, this type test cannot be checked at runtime. Oh, for this union type. This union type can't be checked at runtime. Okay, well, we'll need to fix that. To do, this is now just like an if-else branch. Which then like, what's the point of this method here? When we store, we're storing a value. Where is .value defined? Okay, we have this here. And we don't want to use this version of it. Um, I guess we could do. Hmm. We could just do the dereferencing in here, right? We don't use this. We'll use the same kind of code. So our .value method here is going to return a lit. And we do the dereferencing here. So if it is a register, like I don't like that we are doing the byte checks here. I could at least move this check. I can turn this into like fits U15 method. So if word.fits U15, then we do this stuff. So we'll define that fits U15. And this will be a Boolean. And it's just this right here. So we get the register, and then now we dereference it. So we take registers and we pass in we're doing register from int word. Oh, we already have word.to register, right? Oh, right. We had a to do here. Right. We just referenced we're gonna do it like the other one, so it's gonna be reg.fromInt and pass along our word. So we can remove that to do. And that has its own check right there, so we are checking it. That's gonna be safe. Cool. And then after we get that word from the register, we do .lit, and that does another check. There we go. There we go. How's that? That feels a lot more satisfying, right? We can remove this deref here. That question, I'm gonna, yeah, delete that to do as well. I'm feeling more like this is the way. Okay, so we can store into a register. We can get the value from a register. Cool. That's all our register stuff. Now I think all we need is the stack operations. Oh, we have memory and register safety. Registers, constants, addresses. Yeah, that's all about safety. We've got that down. All right. Oh, let's make sure it compiles. Fits U15 is not a member. Sure it is. Sure it is. We defined it right here. Def fits U15. Okay, great. And register.fromInt doesn't work with a word. Oh, right, we don't need to do that. We can just do word. Like we shouldn't do that here. We can just do w.red and w.lit. Cool. Yeah, I like that the compiler's kind of forcing us to do the right thing here. Wouldn't it be nice if the first time I ran this, it just worked? I doubt that will happen, but it's feeling like that might. It's feeling like the debugging will be minimal. At least these failure cases of like passing around the wrong type of word won't happen to us. All right, let me catch up with you here. You could have written an LLVM backend for Nanto-Tetris. Yeah, you know what? I've always thought about revisiting Nanto-Tetris and just doing the whole stack myself now that I'm more experienced. Because like what would happen in Nanto-Tetris is right you use like a hardware definition language and you write your you know you're basically like using Logisim and you build out your ALU and your CPU architecture, right? But you don't actually run it on that. So for the next step up, you are writing machine code. You're writing like an assembler for a machine code that'll run on that. But then they provide you an emulator that will run that machine code. So I'd like to do it again where I do my own FPGA, right? And when I'm like using the higher levels, I'm not relying on like using their implementation of the VM or whatnot, right? So I think Nanto-Tetris might be worth a revisit someday. And certainly I'd be better at like parsing and compiling and things like that. I could have written that and then run Doom on it, of course. Running Doom generally is the best next step for any project. It'd be cool if someone's run Doom on Synacor. I wonder if that's a thing. I've been writing all this time, but I've not tested all this time. I have not tested anything. So we'll see. We'll see what happens. There will be a moment of truth at some point, and we'll see all the lies I've been telling. Push pop. Do we kind of want to skip the stack stuff for now? No, we don't. We don't. We can be patient. We can unwrap our puzzle one step at a time. To do register check, that is handled. Our registers are now safe. I'm feeling confident about how we're doing that. And now we just need the stack. So let's see. Let's look at our spec. Do you have a screen of rendering or is it just data? I mean, it could be the case that like certain parts of memory are interpreted as like a display output, but we don't know yet. For now, all we know we can do is output characters. So let's look at the architecture spec for push and pop. Push A onto the stack. We've decided A is a literal or a register, so it's A dot value. Let's implement push and pop up here. In fact, let's reorder everything. So everything to do with the program counter. So progress and jump. Great. Um, let's actually put the output stuff up here because that wraps up our state. Um, everything to do with the program counter. Everything to do. This has to do with opcodes. We still have to parse the opcode. So maybe that will be the next step. So everything to do with opcodes and arguments, everything to do with the program counter, everything to do with registers. So that's going to be store and this thing here, this value method, which includes a dereference. And I'm just going to make a dereference method, dereference our reg, and that's going to be a lit. And we'll take this part here. Just because that might come in handy later when we're playing around with our state and inspecting things. So this is just going to be the ref w.register. Okay. So everything to do with registers, everything to do with stacks. So we're going to do def push. We don't know. I guess it's going to return another copy of state. And similarly for pop. Oh, jump. Jump has to do with our program counter. So we'll put that up here. Right next to progress. Okay, all the register stuff here, all the stack stuff, push and pop, and then the memory stuff, read and write. Cool. A bit like Haskell, once code compiles, it often works. That's true, that's the goal here. That's the saying, if it compiles, it works. You think they got nested 4 VMs deep before they ran out of memory? Wait, what got nested? Back when it came out, someone wrote a Synacor challenge VM that runs on the Synacor challenge VM. Oh, that's amazing. That's really cool. Okay. So push, we get a new state. So this dot copy, and now our stack is going to equal, well, what are we pushing onto it? We are pushing on a value, or I think a lit's fine, right? I assume so. I mean, maybe it's used as an address later somehow or something, but we'll see. Stack. No, there's a specific thing for pushing addresses, and that's going to be, what's it called? That's going to be the call and return. So stack is going to equal to L onto stack, right? We're just going to append to the left of the list. What is our stack? It is a list of words. Should it be a list of words? Yeah, let's leave it that way for now. And pop will return a word and a new state. No, it writes the word somewhere. Pop into a register then. Yeah. So our register, and it's going to return a new state. So we're going to do stack.head, and we'll just let that error out. Oh, hold up. I'll catch up with chat in a sec, but I like where it's going. So yeah, stack.head is the thing that we're returning, and we're going to write it into a. So this is going to be store at r the value stack.head. I guess that needs to be a lit, doesn't it? Okay. And this is our yeah, that gives us new state. And I guess this new state is what we're copying with the thing actually popped. So the copy stack equals stack.tail, right? All right. Someone said Idris. If it types if a type checks ship to prod, type safe is safe, right? Yeah. I mean, type safe could mean like stack safe with Idris, exactly. You can make recursion stack safe with Idris. Should we think about all that? Can it not just work? I mean, we got a spec, we want a result. Why should it not work? Exactly. I'm right with you. Okay, so push, we can just use our push method. So push a dot value. That was dangerous. I almost said a dot lit here. That's a possible footgun I've written. So a dot value. Like the types are lying to me in this case. Maybe I shouldn't allow that. Maybe I should actually work with some other type. So we push a dot value, and then we're gonna progress. Like if we really wanted to, we could add type parameters to our state that encode facts about our state, and we could make things like progress be type safe, so that we can only call it in certain states. So you can turn, so basically state here can have a type parameter, right? And in this type parameter, we can have basically some sort of state machine. So that we can only call certain methods if the state is correct, if the state allows it. And that's all like compile time. So like when you compile it, it will fail to compile if it can't do. So you don't have runtime state errors. But that's, I think, a little bit too gratuitous for this. Okay, so we progress and then we have no output. And then when we pop, we can just call pop. And wait, pop does move the element from the top stack, write it into A. So a.reg, pop into a.reg, and then we progress, and then we have no output. Yeah, type state machine, totally. I mean, I have told you the Scala 2 type system was Turing complete. You could do all sorts of fun stuff with it. Okay, cool. Now call and return. Let's take a look at that. So I think it's a similar thing, except just with addresses. Write the value from B into the memory address at A. Write the address of the next instruction. No, that's wrong. Call. Write the address of the next instruction to the stack, and then jump to A. Right, so we write to the stack. So we push a value when we call. So this dot push the address of the next instruction. So we'll get a way to get that. Ooh. Okay, so push works with words then, not necessarily with literals. Or with U15s. Let's say it works with words. Push onto the stack and then jump onto A, and we have no output. So let's look at our push definition. And where we were using it here, we did call a.value. Yeah, any word. Okay, we push words. It's official. Wait, hold on. The way push was written, can you dereference that? Push A onto the stack. It doesn't say push the value of A. So we don't dereference that. Yeah. Okay, what are the functions where we actually do dereference things? So and or mult. Store into A the product of B and C. It makes sense to me that a mult function could reference registers, right? Maybe I'm doing that all wrong. Well, here's the thing. If it's either a if it's supposed to work just with literals, then our code still handles that, right? If it's supposed to work just with registers, our code still handles that. So I think we're safe calling it lit or register. But this push case, I'm really not sure. Okay, we'll try it. We'll try it, but we'll note that this could be a place where this blows up. Yeah, your type system can't help you if you can't describe what's actually supposed to happen. So we push a word. Push word onto stack. And we'll change this definition here. We just push A. And then to do, can we dereference A? That's a potential bug spot. We're not sure yet. And I guess the only way to do that is to just try and run it on the binary. You think it's a literal or a register value? I kind of think so too. Um, I mean, you know what we could do is we could still just do a dot value here, right? And that's a word, and we can push arbitrary words. So it's fine to do a push here of a dot address, right? And just to make sure we've validated things before trying here, word can actually just be address or lit. So these are the things that we're saying that are valid to push in a stack. And that still enforces that we have at least done a checked cast into either address or lit. And then, we erase that again once you push it onto the stack because address and lit are both words. Okay, I think we have a decent solution for that for now. And I think our final opcode, yeah, we've implemented everything. We just need return. Getting really close. Whoops. So we need return. Remove the top element from the stack and jump to it. So we remove the top element and we interpret that as a, oh, okay, we have something to do for an empty stack too. Okay, so I'm not just gonna let that blow up then. We're gonna turn that into an option. So pop should be an option of state. Let's see, we could take the thing that an option of state. Well, let's write on a stub here first, and we can think through that. So when you return, we remove the top element from the stack. So that is a pop. This dot pop. Um, oh, pop. Pop gives us a register. Let's do this. Let's implement pop at the level of our stack type. So I think list already has a pop, so we can do stack.pop. No. Nope. Stack.head option. I don't like going into the implementation details here, so I'll probably change this here. Or like move this somewhere safer. So if there is some value, then you don't actually do anything with it, right? No, that value is going to be an address. I mean, so all we know for now is that it's a word, and we're going to jump to word.address, and then no output, wrap up our state. And then if it's empty, we halt. So this dot halt. Oh, we don't have a halt method. What does halt mean? Halt just means we return none, I suppose. Yeah, we return no new state. Okay. So stack.head option is us basically calling pop. Halt and catch fire indeed. One way to resolve this would be to have an IP register. A register for our instruction pointer. Why would we? I mean, we do already have that stored in our state. I guess in the actual hardware, there would be a register for that, wouldn't there? I mean, that's kind of, oh yeah, that's kind of what's going on here, right? Well, no, when we call, No. Yeah, when we call, we're actually just pushing the address onto the stack. Okay, this is technically correct, or like technically finished, but I'm not satisfied with the way we're doing this push and pop. So let's experiment with the type signature. What if pop just returned the word and the new state? All right. So word tuple with state, and this is all kind of optional. An option of word and state. That's a decent type signature, right? Like in that case, we would do stack dot head option, and now we can map on this case. In this case, we have the word, and then we just return word coupled with a copy of our state. With that head removed. Yeah. Yeah, I think that I can be satisfied with. And we can just write this whole thing as underscore to that. Okay, now in the first place where we used word, we actually have to handle that state here. So this dot pop into a dot register. Oh wait, there's a register argument. So we're just gonna do this dot pop. Wait, not this method. This method here. Wait a second. We'll try that exhaustive match again, because that should be an option. Nope. Why is that? Oh, wait, we have to pop. There's a parameter. Okay. Yeah, because a pop shouldn't really have a parameter, right? You push a thing, a pop, you get a thing. There we go. Which register would you write into? Return this up. You would write the value given by A, right? So we would do our setting. So store into what does it say in our we'll store into a dot register the value. So this is a word, and we just do word dot value. We remove the top element from the stack and write it into A. An empty stack is an error. Oh wait, this isn't just a sum W. This is some. There's a W paired with state. So now we do state.store. Okay, now see this bit here where we're like threading along this state. That's the kind of stuff we get rid of if we did this with a state monad. And maybe that's something we'll do here eventually. But then we have to write our own state monad implementation. I mean, I guess we don't have to. We could pull in libraries, but it's not that hard. And this, we'll just throw triple question mark. So we store, and then we progress with no output. Okay, that feels a little bit more reasonable. Yeah. This whole thing should actually be, it should actually be a try, because then we can have an error case and we can have, I don't know, it's something stacked. Oh, we have an issue here. We had a word, we require an address. And great, the whole thing is compiling. The whole thing is compiling. All right. Right, I removed the register argument. Cool. I see Black Deep with a fun fact. If you let control exit a function without returning a value when you're supposed to, the GCC ARM compiler will insert a hardware panic instruction. That's funny. Okay. Great. Now I want to play around with this. This state I am happy with. I'm happy with this implementation. So let's save that to a new file. So let's open our VM and we'll just do it in the same directory here. And we'll call this VM state. And then we can use our worksheet to play around with the state. So this is going to be in package Synacor. 10x engineer, thank you for follow. Oh, 10x, I saw in chat earlier 100x engineer, so you might have some competition. So we have this state. And I'm going to rename it to VM state. But first we need, I guess we need to import synacor.numbers.star. We need our registers definition. And we need our stack and memory definition. And I suppose we need our opcodes as well. I mean, I guess I just took the whole file. I could just copy paste the whole file. Great. We have our definitions and we have it in a file here. Let's do just a little bit of cleanup. Let's see, all these opcodes, we can erase that. We can make these lines a little bit shorter so it's a little bit easier to read. So after the opcode here, we just, I'm going to put it inside the definition of state. So here we're going to import opcode, well, opcode.star. Oh, we do have one more thing to do. And that is that this step function doesn't need, we should just be getting the opcode from memory. Oh, hold on. Did I forget to put the address of the, I think call might be wrong. So we'll take a look at that in just a sec. Opcode dot, we're going to replace that with empty. You see Scala, you follow? That's great. Great to see another Scala dev in chat. How are we on backseating? Oh, backseating is encouraged. I like helpful backseating. Yeah, we just don't like spoilers, and we don't like any I don't know, pedantic alpha nerding, you know. Okay, there's a to-do. Let's remove more of these opcodes. Opcode dot and replace that with nothing. Make our lines a little bit shorter. Cool. The implementation of return doesn't use pop. It acts as a stack directly. Oh, good catch. Let's take a look at that. Okay, return. Oops. Read memory at address. No. Return. Remove the top element from the stack and jump to it. Okay, return. Remove the top element from this. Oh, yep. We forgot to actually use, yeah, we don't want to use implementation details here. So we are going to use our new pop method. So this dot pop, and then case sum, it's not just some W anymore. It's some W and our like continuation state. Yeah, thanks for that catch. That is totally cool backseating. Highly encouraged. We have our word and we have our state. Now we take the same right-hand side. Okay, what was that here? Except that we jump from this next state, not from this state. And in case of none, we halt. Okay. And you know, this here, could just be a map. And it's going to be case, there's a tuple. Yeah, there we go. And we don't need that none to none line. Oh, no. Oop, this stop popped on map. There we go. Are we back to compiling? No. We have a slight issue here. Found some required. Oh, this is weird. What did I do wrong? So we found none.type is Synacor state. We needed an option of character. So no output should return like a none of character, right? So here, yeah, like this returns a, I mean, yeah, it returns that same output type. Let's give that a type. Let's give our whole return type a name. So this thing here, we can call this our step. We can call it our tick. I like tick. So I want to take a quick aside and mention this. So I keep saying that this is a state monad. This can actually just be, oh, hold on, before I do that, we'll get there later. Let's just fix this. So this no output is supposed to return a tick, and output also returns a full tick. They are kind of our terminal state transformations. And this whole thing returns a tick as well. So if no output is returning a tick, then what's the issue here? Expected tick, we found a tick, and we required a tuple. Oh, I see. Yeah, I was being silly here. This should just be a match. Right, because otherwise you'd have to flatten it. I suppose it's a flat map. This is a flat map. I'm being silly. Pop.flat map. There we go. I don't know. I guess doing the match is more explicit, but we forgot that no output already wraps up in a state. And otherwise it halts. So no output like progresses our. Yeah, no. We still have to progress. So we gotta do dot progress based on our opcode and then no output. Alrighty. Now, are we always progressing? We're either progressing or jumping. See, if I were doing this as a state machine, um, I would have like progress and jump would be methods that change the type parameter state to like has moved, right? And if every instruction must move, then we can enforce that. We can force that either one of jump or progress has been called on the state. So that kind of thing you can do in the type system to make it safe. Good morning. My call is pushing the wrong address. It should be your PC after incrementing. Oh, okay. Good catch. Okay, write the address of the next instruction to the stack and then jump to it. The address of the next instruction. So call this dot push not a address. Right, the next instruction is going to be based on our program counter. So it's going to be PC dot incremented, right? PC. Well, it depends on the number of parameters. So it's going to be PC dot inc1. It's going to be precisely the thing that progress would progress to. So I don't want to mess around with the low level details here. So I'm gonna make that a little helper. So def next instruction. I guess we can do like next PC. No, we'll just do next instruction. And it would basically be this minus the copy bit, right? So do that. So the next instruction, if there are just that. Depends on the number of parameters. And now this method becomes simplified, and it basically just becomes take our state and we copy where program counter equals next instruction. Yeah, next instruction does require the opcode as a parameter. But opcode is kind of global. We're going to remove all the opcode parameters in just a second. Progress and jump. Yeah, we're going to remove all the opcode parameters. Okay, so now all of these up here, we're pushing next address. Next address. Not found next address. Right. Next instruction. There we go. Alrighty. Great. Everything's compiling. Everything's implemented. The one last bit is opcode. So, um, yeah, we actually have yet to parse the opcode from a word. So we'll do that. Um, let's do it up here. So everything related to arguments. So these are the three arguments and def op. So opcode. Now we take the memory, and then our opcode enum needs to be able to take from memory. So object opcode, not from word, I suppose. Okay, we'll leave that unimplemented for right now. Oh, sorry, I had that covered up. And just use it everywhere else in here first. So opcode is going to be memory, memory at this address at program counter, and then opcode from there. Opcode dot word memory at this program counter. Great. I have that as a def. I think it probably should just be a val. It should always exist, right? Yeah, if your program counter is valid. Actually, I'm not going to do that because say we generate a new state that is invalid. I don't want it to crash right there. I want to be able to examine that state. So that's like an optimization we can do later. But now step. Step doesn't need an opcode parameter. Progress doesn't need an opcode parameter. So we're going to take all our progress op and just replace that with progress, right? Okay. Def progress. We can take that out of here. Cool. And the next instruction doesn't need a parameter either. Okay. Okay, so everything related to our current frame is right here. Our three potential arguments, as well as what's next and what's current. And when we progress, we jump to the next instruction. When we jump to an arbitrary address. Cool. We've got that. Oh wait, no, there is a compile error still. We still haven't. Oh, what's going on here? Def from word. There we go. Okay, now we just need to implement this. It's almost a moment of truth. It's almost a moment of truth. We still have to, let's see, we still have to extract our binary, and then we still have to extract our output from our running program. I think we can do that by the top of the hour. We are pretty close. So now the word. Let's see. Let's look at our architecture spec. I'll leave that on screen for a sec while I get some water. All right. Binary format. We have opcodes. I suppose we just take the word at the current address is our oh yeah, of course. All right. um, I mean, well, we knew that much. We already did that, right? The word at our current address is our opcode. Um, we just need to turn this into an int, and then we can use. So opcode should have like from ordinal. So opcode from ordinal. And as long as these enumerations are defined in the right order, that should just match up. And we could just do word as instance of int. Word.toInt. So we have a toInt. Let's add that to our number system. So our number system is in vm.scala. For some reason, we should rename that. So extensions on word as character def toInt. You know what? I don't like converting a word to an int. But I don't think these words, these numbers need to be aware of opcode. I suppose we need it at some point, right? Mm, I think instead we should do the same pattern we've been doing here. So word can be interpreted as an address, a literal, or a register. Let's define op, and this would return an opcode. And then now let's take this out. We'll put our implementation down here. So this is the opcode.fromOrdinal, and w is just an int, so that just works. Cool. That's easy. Right. Let's do. This just makes everything inside a Synacor accessible here, which maybe bites us later, but it gives us that. And then now up here, we just do we just get memory at a program counter and we do dot op. And from ordinal should have its own like exception that it throws. I'll just rely on that one. Can a Scala enumeration have an explicit numbering? I don't know if you can override it. Yeah, I'm not sure if you can override it. I mean, you probably can, right? Like it probably implements some sort of type class or extends some traits or something. And you could probably override your ordinal. Or you could probably just straight up override the from ordinal function. That's what I imagine. But I won't look that up right now. But usually I've found that just listing them in order is fine. You know, the spec listed in a pretty reasonable order where like I like this grouping here. And we go back to our playground. And it's time to play with, whoops. time to play with our state VM. So we'll need, I suppose, a way to initialize it. Let's just initialize it here. Um, I guess we'd initialize it from the memory stuff. So what is it? I guess you get class dot. I want to get the resource as an input stream. So this name is going to be Synacor slash challenge.bin. And I'm going to wrap that with the util.using since it is a resource and needs to be closed and all that. Okay. And then we have an input stream. Expected fewer braces. What are you talking about? So input stream. And we want the bytes. Here are all the bytes. And now our memory implementation. Right. I think I want a vector. So our addresses are secretly ints. And I think we just want our underlying type can just be a vector. I mean, we could load. I just don't want to use a map for this. Okay, so we have an array. Val a equals input stream dot read all bytes. And actually, it's already trying to interpret that. Null pointer exception. That name there is probably wrong. Get resources streams core slash challenge.bin. Let me look in my terminal down here at the bottom. Source main resources. Synacor challenge.bin. That is it. We can debug that later. Do the glasses give a red tint to my code? Yeah, it's like analog redshift. I think my monitor might be doing that too. But when I have these lights on me on stream, they are really bright. So it gives a red tint to everything. It's actually really fun to wear. It makes everything look kind of nice. It makes sunset last longer. And it hides my bloodshot eyes from sleep deprivation. So this array we're gonna put into a vector. We need the underlying. Let's just initialize an array. So we'll call this bytes. So val bytes, and val our array is going to be array dot dimension of dimension. So this is going to be an array of word, which is secretly an array of int. Of size. What's our maximum address? So 0x8000. Yeah, that covers all of the 15-bit numbers. Yeah, thanks. I have pretty good key lights here. Okay, we have an array initialized to 0. And let's look at our number system. We had a method here that got from bytes, word.fromBytes. Okay, so we're going to iterate over the indices of our bytes array, I suppose. Let's do some checks on our bytes array. So I'll do some assertions rather. So bytes.size is, well, I suppose size mod 2. There should be pairs of bytes, so this should be 0, right? Just encoding our assumptions here. Our other assumption is that the size is less than or equal to maximum memory. All right. Okay. Now, given that, we can just iterate over an indices of the array. So we can take bytes indices. So for I in bytes.indices, do. Why is high byte calculation use 4-bit shift? One, oh, good catch. Probably because I was thinking about hexadecimal or something, but then it would have just been 2. Yeah, it should be 8, exactly. Byte, not a nibble. Okay. Oh, no, no, no. This is going to be double that. Size is going to be less times 2. So times 2 is going to be, I suppose, 1, 0, 0, 0. Yeah. And this is going to be our array size. So we're just gonna we're just gonna initialize that regardless. And since we have 2 byte indices per every array index, then that should be double of this. I should say like times 2 or something to make that like explicit. Now for every byte index, we're gonna get a byte and its adjacent one. So val high byte is gonna be no. It's little endian, so the low bytes first. So low is gonna be the byte at bytes at that index. And then that index plus 1 is going to be the high byte, right? Oh, no. We want 2 times I. 2 times I. We're going to do bytes.indices.by 2. Right. So that low is I. And then high is going to be I plus 1. So our word then is. Oh, let's just mask this here. 0xff. And then that's. So when you mask things, that casts it into an int. So now it's no longer like a signed byte, and we should be able to hold that fine. So our word is going to be high left by 8, and or that with low. Yeah. Uh, it's exactly this code here we're implementing earlier. I should just do from bytes here. So word dot from bytes I and bytes I plus 1. And then array at what index? I suppose at the index divided by 2. I over 2. So array at that value should just be that word. Cool. And then we turn that into our memory. So let's look back at our memory implementation, our memory type here. I don't think anything will change here if we just make that a vector. Well, Now let's make that a little case class with an underlying vector. So case class memory. So underline is going to be a vector of word. And where did we use this? So memory dot, we only ever use it with apply and updated. Okay. So def apply. So given an address, given an address A, we just convert that into an int. So a dot to int. And then get that from the vector. So from the underlying. I'm feeling lazy. I'm just gonna do a dot as instance of. Or you know what? We can do the same thing we did before and just do like a as index method. So we had an as index. Wait, index? We had a to index method for registers. Let's do the same thing for address. That way we're converting to int with a purpose. Because we don't really want to treat addresses like ints in any other case, except when it's an index. So in this case, an address is 15-bit. So we also mask it. Wait, what happened here? When we turn register into an index, this isn't correct. Is it correct? Oh yeah, because we only keep within the first 15 bits. We're ignoring the 16th bit. That's what's going on there. Yeah, sure. It's literally the same implementation then. To index. Yeah, great. Oh wait, that should be in the extension methods for address. We can make more things inline. Okay, now we can do a dot to index and index into our underlying vector, and then def updated. So given an address at which to update and a word with which to update, and return a new vector. So this gives us a word. We return a new vector, and we just use our underlying vector. Or no, we're returning a new memory. Updated at an index a dot to index, and the element w. Okay, looks like we might have a compile issue here. Oh, to index. Oh, this is a double definition because that erases to the same thing. I suppose we can just put to index on a word. The masking actually matters for register. Okay, I'm gonna do a dirty little trick just so we can move on. And I'm just gonna pass like a dummy implicit parameters. They have different type signatures. So using dummy implicit, there we go. Now it compiles. Because now these aren't the same method signature, because both of these erase to int, right? But if you put in an implicit parameter, then it's a different function. Alrighty, so we have a memory implementation, and let's do that in our playground. So this compiles fine. So val memory. So we're going to take our a, put it into vector a dot to vector. We're going to wrap that in memory. Okay, we could look at some values in there. So memory dot get. Oh, and we still have the wrong string there. Okay, we'll fix that eventually. It's the top of the hour, and we're not done yet. I thought we'd be done. But we're close. Stack, I don't think we need to re-implement. So we do have a way to get memory out. Now we just need to load up our state. So we'll get our initial state. And our state needs a program counter. So program counter is going to be address from int 0. Registers is going to be registers. How's register defined with an underlying I array of word. I think I'm going to give registers an empty function or init. So def init gives us registers. And it's going to be registers. Well, it's going to be like this here. With 000 words. Let's see. Word dot from int 0. Now z equals that. So z. I suppose we could do an array that. Well, we can do an array that fill. Array. So I array dot fill, and we're filling with 8 zeros. That property. Registers dot init. Great. And then what do we have next? A stack. So our stack is just going to be an empty list. So that can just be nil. And memory. And this can be memory.get, which throws an error. So val, we'll call it start. Our start state equals that. And the last thing, I did want to name this state. And we named up to VM state. There we go. Now we can match the file name up here. Maybe. Okay. VM state does not exist. Oh, VM. No, that's it. VM state. It just needs to recompile. Yeah. Let me copy paste that very explicitly. I found, well, the worksheet hasn't gotten this yet. Is this compiling properly? Okay, well, it's state until it errors otherwise. Oh, okay, now it's up to date. Okay, so we're getting the null pointer exception from the get resource as stream. So in get resource as stream, we have the resource name. Let's see if anyone's familiar with the JVM here. I think I'm doing that right. I think you can use a relative path, right? Maybe I have to use an absolute path. Let's see. That's not the kind of thing we need to debug. So let's ask ChatGPT here. So we have a project, and we have a file. Let's just copy the address here from our terminal. Write this here. Oh, I can't really copy paste that. Okay, we'll type it in. We have a file source main resources Synacor/challenge.bin in an SBT project. I want to load this file with get resource as stream. Control Shift C. I don't know. I don't have like highlighting here in the same way. Maybe that was it. Oh yeah, that was it. That was it. Thank you. The correct resource path is Synacor/challenge.bin. Okay, yeah, great. Well, I have that. So via get class, get resources stream, I'm not going to do a null check here, but we are doing the same thing, yeah? Yeah. Let me just copy paste it explicitly. So it is the relative path. That should be fine. Oh yeah, and when I highlight it, those are exactly the same. So it could just be that my worksheet state doesn't have that in the class loader. Okay, what we're gonna do is make a main state, a main file. Do I need a leading Synacor in the file name? Yeah, so I think it's relative to all the resources, right? Um, so this file is in like source main Scala, and then the file that I'm getting is in source main resources, and they're both under Synacor. So I think it is this relative path. But my guess is that right now our class loader isn't correctly loading the resources. No, if you look at my Advent code, so let's look at, I don't know, day 11 from 2025. We do it from resource, and we do the same kind of thing. This is the relative directory from the resources directory. And this is the relative file path from the resources directory. Like we could try to do, let's just try to do this with it and see if that fails. We're so close. Oh, okay. Hey, this works just fine. Oh wait, no, no. It's not the same thing. So instead of 2025, it's Synacor. Instead of day 11, it's challenge.bin. And hey, that loads up just fine. In fact, let's just look at the first character. Oh wait, next. Malformed exception, input length. That might not be a valid character, I suppose. I mean, it's an iterator of strings, and the first one should be a string. Hmm. Yeah, I mean, it's a binary. I don't expect it to be. Well, I mean, you could interpret all the strings, but I don't expect it to be like nice Unicode. And maybe there's some issue there. Read as binary. I mean, I'm reading as bytes, right? That's what I'm doing here. Oh, you mean from on my IO resources here? Yeah, get lines probably doesn't work. But we can do an iterator of characters. So I guess I would take the first two bytes and interpret it as a character. We can do that next. And that will return. It's not a valid character. Can we get all the bytes from here? We can't get all the bytes from here. That's why we're using this other method here. Right, like this is for loading up strings and bytes and whatnot. But the point is, that resource does exist at that path. And we're using the same path here. Okay, this isn't the kind of thing you really want to fight. Via the class loader, no slash ever. Okay, current thread get content. Wait, you should just be able to get class. Things that will not work, common foot guns. If you want to verify SPT, actually put it on the class path. Okay, here. It's a good debugging trick. Okay, it is on the class path, so it exists. It exists, so we know the class loader is not messing with us. But when we do memory.get, we get a null resource. The file. Okay, so we're gonna debug this with ChatGPT then. So I was able to get I was able to verify the file, but when I get the input stream, then what is happening? We fail with a null pointer exception. All right, you're calling the method on a null. Well, no, the point is that this here, where does it actually come from? Let's follow the stack trace. Oh, that's not very helpful. Yeah, null resource. Let's modify this init. We have a null resource. That's almost always you're asking a different loader than the one that found it. Okay, let's do this then. Thread.current thread, get context class loader. All right, get context class loader. Let's make sure that works. Non-legal formal parameter for a function literal. I think we have an extra paren somewhere. Thread.current thread. We have to do that. Get context class loader, get resource as string. Oh, get resource. Oh, can we do get resource as stream? So we can get resource for sure. So we should be able to get resource as stream, right? And then we should be able to like read all bytes on that. That read all bytes. Let's just comment this all up now and mess around with this. Oh, we need to have our Synacor challenge. Are we able to do that successfully? Okay. Get read all bytes. Read all bytes. Okay, cool. That seems to have worked. Great. I guess that's what we have to do. All right. So this is our. We'll just copy paste that whole thing together. So using that. Okay, well, that was fun to debug. It's not /Synacor/challenge.bin because it is relative to the resources directory. But I think val memory equals what? Oh, wait. You just have a weird syntax error here. All right. Not legal formal parameter for a function literal. Here on this side. So def resource. We're just gonna make this here separate. So this part we know that worked. Okay. Hey, that worked. That worked. Cool. We have our memory loaded. Alrighty, alrighty. We are so close. I say 5-10 minutes away. Yep, we're getting bytes. Well, actually, no, memory. Those aren't bytes. Those are the words. So that's already been interpreted. And now we can uncover our start state. Cool. And we could do start.step to see our next state. Yay. Okay, it's working. We were able to execute the first instruction. And now we want all the outputs here, right? So how are we going to do this? When we step, we have this option of our output and state. So this is an unfold. So val states equals lazy list dot unfold. Starting from our start state, and our state transition function is just dot step. And this should return a list of not nothing. This should return a lazy list of our optional outputs. And we can just flatten that. Oh, is this failing to complete? Oh, that's a hot minute to execute. Or maybe it just took a second to update. Okay, great. So we have a lazy list of optional outputs. We're just gonna do states dot flatten, I suppose. So we'll make this def states. Def states, we don't need a lazy list yet. So iterator dot unfold. And this becomes an iterator of characters. We're gonna take our states and we're gonna flatten. Oh, states out flatten. Now it's an iterator of characters. And then we're just gonna make string of that. And it's evaluating the worksheet. It's taking 7, 8. It's taking a few seconds. So we'll probably want to be running that for one in like a separate file. And running it from the REPL. Oh, this is taking a lot longer than it did earlier. Something's wrong. Probably flatten and make string was not good. So we can do states.flatten.for each. How about this? We just print something when it's actually a thing. So we'll do states.for each. Case none. Yeah, if there's no output, we do nothing. Case sum character. In this case, we're gonna print that character. I am expecting it to halt, yeah. And it did halt. Like I was able. Oh, right. I never actually ran the iterator. I suppose I am expecting it to halt. What I could do is print them one at a time. Yeah, it's not able to run all the way through there. Okay, so let's cancel this evaluation. We don't want that. And I can feel the lag. I can feel we're killing our machine. And we have a wait, we're in main.scala. What files do we have? So ls. Oh, what does my in do? I have no input. I did not implement in. Okay, there it is. So we are not done yet. We are not done with all the opcodes. Yeah, there's input. Our in state just hangs, completely hangs. No output, it doesn't even progress. So whatever I loaded is killing the stream. Kill all Java. Quick. Okay, can you still hear me? We just killed Java. God, I hate that. Yeah, kill all dash 9 Java. We got it. Um, we'll restart VS Code too. These worksheets. It seems like terminating the evaluation in worksheets is impossible sometimes. They've got, I don't know, I should really talk with the maintainers and try to figure out what's going on there. I don't make a habit of killing Java when I can't compile or like run a project. That's just in the worksheets. You can still hear me, that's good. My return is calling jump and then progress. Ooh, good call. Yeah, we shouldn't be jumping and progressing. So that'll definitely skip an instruction. Good catch. You had some good eyes on code today. Okay, so in our VM state, we need to implement ret. Is my video still lagging? This might have to be the part I save for tomorrow. We're so close, but we might have to save it for tomorrow. Um, and I'm gonna have to sit and like wait and not do the input because I don't want to spoil myself before the stream. Okay, things are working. All right. I don't know, my computer feels pretty laggy. It's not throttling, but there is a process going crazy. And it feels like it processes maybe the JVM. Well, okay, things are back to normal. Things are not back to normal. All right, well, let's go down here. So return should not progress after jumping. See, I should make a state machine for this. That is invalid code. Yeah, I'll resist. Eric, there's a chance you won't be able to make it. So I'll have to do a reenactment of my reaction. Fair. Um, I mean, for everyone else for whom I'm not performing the reenactment, I do have VODs. So that's gonna be on YouTube. So I'm dual streaming this to YouTube right now, and then they get saved there permanently. Everything on Twitch disappears eventually. And this year I'm putting more effort into stuff, so I'll edit things, I'll tag chapters, and yeah, I'll make kind of summary videos that don't have all the pausing and thinking. Everything is in error right now. It's already defined in main. Oh, right, we started making a main file because we want to put our worksheet code here. So package Synacor at main def main. Okay, and let's open up our worksheet. We'll move this stuff here. Yeah, just copy all of it. We don't want to do that in the worksheet. Okay, we can just .get on that. Okay, so we have our state. Um, and we can't run it yet. We can't run it. So we go to our VM state. Let's implement out. I think if we don't run the code, I at least want to implement all of our opcodes. We want our architecture spec. So what does in even do? Read a character from the terminal and write its ASCII code to A. It can be assumed that once input starts, it will continue until a new line is encountered. This means that you can safely read whole lines from the keyboard and trust that they will be fully read. Oh, okay, so we have to find a way to like wire that in. Because I'm not going to put it right in here. I'm not going to use system.in from here. I suppose. I suppose we could pass in an input stream to our state. Or we could do like an iterator. We can do an iterator of input. And then we'll have to have some sort of execution loop in our main class. So I'm not sure how I want to do input until I see what our main class looks like, or our main method looks like. So we need to import numbers. Oh, I could totally just alias it to halt. Right. Yes, not everything is needed. Okay. Okay. So we'll get to see the code or the message. So in this .no output, this is going to be a to do, and if we do that triple question mark, it will still compile, but it'll throw an exception instead of just hanging in an infinite loop. We prefer that. And our case halt will be case halt or in. We do nothing. Good hack. Good hack. Thank you for that suggestion. Oh, hold on. That's all caps. Infinite loop exception. Yep, we've solved the halting problem. So memory found units. Wait, what? This dot get. Wait, this get returns our units. Oh, we erased the line where we actually construct the memory. So we have memory from a.to vector, right? Incremental wins. So I suppose the next night will be input and designing like our user interface so that we can interact with the VM. So states, we're gonna do iterator.iterate starting from our start state and loading the next state up with .step. Or rather, wait, we're unfolding. We're unfolding. And I suppose we can flatten .make string. Oh, you know what I'm gonna do? Let's flatten it. And then we're gonna do a for each. So for each character, we are going to print that character and let's sleep like a millisecond or something. That's 1,000 characters in 1 second. Let's sleep like 5 milliseconds. So we're printing 200 characters per second. No, we'll sleep. Let's sleep 100 milliseconds. So we'll print the character and then we'll sleep, and then we can print line at the end. And discarded non-unit type. Wait, really? That's just a warning. We can ignore that, but this ch is not value. Go. Oh, thread.sleep. Sorry, thread.sleep. Okay. Now let's pull out a terminal. Moment of truth. Where is Velox? Oh, I should just really have an SBT daemon running, so I don't have to wait for the startup. But then I have to not kill all Java too. I have not really watched Velox. What's he playing? Or what are they playing? Case in. Yes, that's an unreachable case. Good. All right. So we're gonna run main Synacor dot main. Yeah. Welcome to the Synacor challenge. Please record your progress by putting codes like this one into the challenge website. We got a code. Executing self-test. He DJs the Advent Code Day 1 party every year. Oh, cool. You have a Day 1 party. Do you have an after party? I'm glad you like the delay. I don't know what it's doing here though. The delay might be too much for the for the self-test. I don't know what happens after this. Yeah. You know, for next stream, I should change my terminal color scheme so that it matches Synacor. I think I'll do that. You know what? I think it's just halted. Right, it printed a new line. Yeah, I think it's just... No, it's not done. I think it's just hanging. I don't know. I don't know. Anyway, I think that counts as a win. I think that's working. And next time we do input, I guess we have to figure out why. Oh, I think that's the first puzzle. I think we have to figure out how to fix the self-test. Figure out why it's hanging, why it's stalling there. So that will be cool. It probably halted on input or something. Yes, I will git commit that, and then I'll add some notes from the stream so that people can keep up with what's happening. And yeah, well, we'll find someone to raid. So the VM definitely can produce codes that are not valid. So don't assume every code you see is a success. Oh, okay, that's fair. Yeah, check the codes. Yeah, I have to look at the repo. Oh, oh my pointer is stuck again. You know, it might just be the case that When I think my computer's lagging, it's just my keyboard that's lagging. All right, so I'm gonna go to the repo. Yeah, I think I need to halt this I need to halt this execution. But I need my code before I do that. Okay, we got our code. Um, let's test it. So here's the MD5 sum. So MD5 sum of echo that. And 0f something. Oh, that doesn't look right. Echo dash n. Oh, okay, cool. There is a code. I think that matches. Yep. Echo's adding the new line. Fair. Cool. Well, we got it. We got it. Part one. Part one done. Oh, let's find someone to raid. That was fun. That was fun. I'm excited. uh, thank you, thank you. Thank you for thank you, Eric, for making this. Thank you, Zuno, for reminding me that exists and I need to do it. It's a perfect idea for this year. Okay. Uh, oh, Liquid Cake is on doing part two, an upgrade on part two. This will be interesting. I don't want to be spoiled by this because I still need to do my own upgrade on part two. But I'm sure this is great. All right, so we'll raid Liquid Cake 1. And yeah, thanks to who was that rated? Oh, I can't remember your name. I'm sorry. Um, Zede Shah. Yeah, thanks for the raid, and thanks to everyone who's new for sticking around. Had a lot of fun with this. Okay, let's say hi to Liquid Cake.